Hi, how are you doing? Welcome to this lesson. What we're going to be looking at today is bounds for compound measures. So, bounds for compound measures. Right, now you have to have seen upper and lower bounds videos before, or you have to know upper and lower bounds before you get to this, because now what we're going to be doing is combining the upper and lower bounds, okay? And there's a whole table that I've got in the notes where it says you can learn it off by heart. The lower bound, upper bound of an addition is upper bound plus upper bound. The lower bound of an addition is upper bound plus lower bound plus lower bound, yada yada. And you can learn the whole thing there. What I'm going to try and do is I'm going to try to explain this using a measurement. Okay? Because I find that if you can understand what we're talking about here, it's much easier to follow and to remember what the upper bound and lower bound is. Alright, so let's say we've got this measurement, okay? And we've got some kind of measurement, and I measure it. The red is the exact measurement. So this is the exact measurement there, and that's the exact measurement there, okay? Alright, and I want to say, okay, well, great. What is the upper bound of this one? What is the biggest mistake I could make? Well, the biggest mistake, I'll do the upper bounds in blue, okay? The biggest mistake would be if I was like a half above. So there's the biggest mistake there. Let me do it freehand, no need to use a ruler. Okay. If I was a half above, that would be the biggest mistake of this red one. Well, what would be the biggest mistake of this one on this side? Well, it would also be a half above, half a measurement above. Remember, upper bounds, half above. Well, what would be the biggest mistake? The lowest mistake I could possibly do? Well, the lowest mistake would be a half below, which I'm doing in green. And the lowest mistake would be a half below. So the red is the 100% accurate. If I was measuring with a microscope, okay, and I was going right down into it, that would be the red, exact accurate, the atomic measurement, okay. But I always know that whenever I measure something, there's always a mistake. There's a rounding error that I've incurred because I only need to be certain. I only need a certain degree of accuracy. So I know that I've made a mistake. So this would be the upper bound, the half above that would round down to this, or the lower bound, the half below that would round up to that. Fantastic. So I say. Now it's a little bit difficult to describe this with times and divide, but I'm going to do it with addition. Okay. So I say, okay, if I've got this measurement and I add it on to this measurement, okay, what's the biggest mistake? What's the upper bound of that addition? Well, the upper bound of that addition would be this biggest mistake, okay, right, plus this biggest mistake. So the addition would be the two mistakes compounded, added together, right? Are you with me? And same for the lower bound. Will it be that smallest mistake plus that smallest mistake, so the lower bounds would be compounded, the two mistakes would be compounded. You with me? The thing comes with subtraction. And for subtraction, it's okay, if I want that distance from there to there minus this distance, okay, what's the biggest mistake I could have? What's the upper bound of the subtraction? So what would be the upper bound of, let's call this x and let's call this y. What would be the upper bound of y minus x? Well, how could I possibly make this as big as possible? Okay? Well, to make this as big as possible, I want this distance to be as big as possible. Well, the distance that will make it as big as possible is from there all the way to there. That would make that the biggest distance. Upper bound of the difference. Well, what is that? That is the upper bound of y, right, minus the lower bound of x. That would make that distance the biggest. That would make the biggest mistake, the upper bound of the difference. You with me? Now, what would be possibly the lower bound of the difference? Let's see if this is visible. What would be the lower bound of the difference? Well, the lower bound, I wonder if that's too light for you to see. I hope not. Let's see. The lower bound will be, how do I make this the smallest? Okay, the lower bound of y minus x would be, how do I make it the smallest? Well, all I need to do then is take a look at the smallest distance that I have here. Well, what's the smallest distance? It's the lower bound of y, right, there, minus the upper bound here of x, minus the upper bound of x. That would make that distance, the smallest error. Are you with me? Okay. Now, That's for addition, where it's compounded. It's for subtraction, where it is, you find the difference, right? For multiplication, okay, the error is also compounded. If I made a small error times by another small error, that error is compounded. Are you with me? For division, right, the error is similar to this. How do I make, now think about this very quickly, because I'm going to show you a trick in a second of how to remember this. How do I make the upper bound of y divided by x? Well, in order to make this a fraction as big as possible, I want to make a big fraction, right? I want a bigger number on top and a smaller number at the bottom. Okay? The smaller your denominator is and the bigger your numerator is, the bigger your fraction. So I want a bigger number on top, biggest on top, divided by a smaller number at the bottom. Right, to make this fraction as big as possible. To make the fraction as small as possible, well, the smaller you make a fraction means the larger you make the denominator, the smaller you make the numerator. For example, a half is bigger than a quarter. And if I want to make that smaller, I do 1/8, 1/16, 1/32. And as I make that smaller, so it goes down. Alright. So I want a small number on top divided by a big number at the bottom. Okay. Now, that's the understanding. The easy way to remember, well, I think it's slightly easy, is that if I've got the positive operations, and I call them positive, but if I've got something that makes something bigger, plus and times, alright, then the lower bound is lower bound, upper bound is upper bound, upper bound. Alright, for plus and times. If I've got the difference operations, maybe difference is not the right word, but the difference operations where things are being made smaller, alright, like subtraction and division, alright, then the upper bound is upper bound alternate lower bound, and the lower bound is lower bound alternate upper bound. For both of them, watch. Upper bound alternate lower bound, lower bound alternate upper bound. Okay, so that's a shortcut trick to remember it. Okay, for the difference operations, I start with the same and I alternate to the opposite. All right. For the addition operations, it's just same. All right, cool. So on the next page there, I go through a whole spiel with two measurements and working out the upper bound and lower bound of that. I've got x is 3.4 to 1 decimal place, y is 1.8 to 1 decimal place. Find them added together, subtracted, multiplied, divided. There's the whole thing there. You can go through and look at that, okay? That's very specific. It's just using those combinations, okay? What I do want to look at, however, is the last example there of that big compound division that I've got there, the EG, right? And with this, I've got H equals V squared times by sine of D squared all over 2G, right? Okay, so we say here's the measurements for this. Well, firstly, V is 250 to 3 significant figures, right? 3 significant figures. It means I start counting here. 1, 2, 3. Okay, so that means I looked at my 4th significant figure to move that. Okay. D is 72 to 2 significant figures. All right. 7, 2. So I looked at point 0 to round it. Okay. And G is 9.81. 9G is 9.81 gravity to 2 decimal places, right? So 1, 2, that means I looked at my 3rd decimal place. And they say, what is the upper bound of this? Okay, right. So what is the upper bound of this? The UB of H. Well, for upper bound, right, now for upper bound, I need the biggest number on top divided by the smallest number at the bottom to make it upper bound of a fraction. Okay, so I need now the upper bound of V, right? Are you with me? Squared, right? And then sine of the upper bound, because I wanted some multiplication of D squared. With me? All divided by, now I want the smallest fraction at the bottom, 2 times the lower bound of G. I want this as small as I possibly can get. Okay? Right. Then, if you look on the notes, the upper bound of this Well, the upper bound of this is half above, so 250.5 squared, right? The upper bound of this is half above, 72.5 squared, with me? And the lower bound of this is half below, 9.805. Are you with me? Put it into your calculator and you get out this. 2910.5621. Okay, I'm leaving it to that many decimal places because I want to show you something in a second. Okay, fantastic. Right, then they said, okay, right, super, that's the upper bound, sir. Find me, please, the lower bound of this whole thing. Lower bound of h, right? Well, the lower bound of it, all right, I want for a fraction, I want the smallest number on top divided by the biggest number at the bottom. Okay, so, and on top I've got multiplication, so I want the lower bound on top, lower bound of b squared, times by sine of the lower bound of d. Multiplication here, so I use same with me to make it as small as possible. Alright? Over 2 times the biggest number at the bottom, upper bound of g at the bottom. Are you with me? So that's what I'm thinking about for this. I want the fraction to be as small as possible for the lower bound. So I want the smallest possible number on the top divided by the biggest possible number at the bottom. Okay? And now I just put those in as well. So if I look at this. So the lower bound of this is half below, right? So 249.5, half below, right? The lower bound of this is half below, 271.5, with me? And then half of this, upper bound of this is half above, 9.815, half above. You with me? Plug it all into your calculator and you get 2851.8978, yada yada yada, forever. Okay. And they say, great, super, there's your upper bound, there's your lower bound. What would be an accurate rounding? What would be an accurate rounding for this measurement? Okay, and as accurate as possible. Alright? Taking into account your 2 errors. Well, my most accurate possibility is, what do these two both round to? What's the smallest number that these two will both round to? Okay, so, well, 2,000, okay. 2,800 round to 3,000, 2,900 round to 3,000. So 3,000 would work, but it's quite big. It's not the smallest number. Let's move on. 2,910. Well, that will round to 2,900. Okay. 2,851. Well, that will also round to 2,900. So 2,900 is more accurate than 3,000. Great. Let's try the tens now. 2,910. Well, this rounds to 2,910. 2,851. Well, this round will round to 2,850. Let me stop. They don't round to the same number. When I round it to the nearest 10. You with me? They round. The closest I can get is to the nearest 100. So the closest, most accurate that I could possibly be with this is h equals 2,900, because that's what both the lower bound of h and the upper bound of h both round to. Okay, it's kind of confusing, huh? Yeah, I know. This is something that really catches kids whenever we teach it, okay, whenever we go through it, it really catches them. I suggest you go look at the notes carefully, because I've skipped quite a few steps here in order to compress it into 10 minutes, okay? Go look at the notes carefully, go follow them, maybe even write them out yourself to make sure that you've got everything on your page, okay? And then watch this again. Definitely, I would suggest watching this again, if not 2 more times, okay? But, as you know, I'm always here for you, so you can come watch again, okay?